T11.12. As a non-native English speaker, Sanda is convinced that people find more grammar and spelling mistakes in essays when they think the writer is a non-native English speaker. To test this, she randomly sorts a group of 60 volunteers into two groups of 30. Both groups are given the same paragraph to read. One group is told that the author of the paragraph is someone whose native language is not English. The other group is told nothing about the author. The subjects are asked to count the number of spelling and grammar mistakes in the paragraph. While the two groups found about the same number of real mistakes in the passage, the number of things that were incorrectly identified as mistakes was more interesting. Some numerical summaries of the data follow. Right, so a couple things I want to highlight here. We had random sorting, which is equivalent to random assignment. Let's see, 30 in each group. Actually, we don't need to highlight it there because it's in the table here. So the group that was told the author was a non-native speaker is going to be group number 1, and then the other group will be group number 2. All right, part A. Is there convincing evidence at the 5% significance level that the mean number of mistakes found will be greater when people like these volunteers are told that the author is a non-native speaker? All right, so we're going to follow the 4-step process. First, we're going to choose the procedure. This is a 2-sample t-test for mu1 minus mu2. Okay, our parameter is mu1 minus mu2, which represents the true difference in mean number of mistakes found, and it's the non-native treatment minus the no info treatment. Okay, right, our hypotheses. The null hypothesis is that basically it's a statement that's equivalent to there's no difference, right? So if there's no difference, then mu1 minus mu2 would just be 0. The alternative hypothesis is going to be a statement equivalent to there being a greater number of mistakes when people are told it's a non-native English speaker. So that'll be mu1 minus mu2 greater than 0. Okay. Right, our statistic is x bar 1 minus x bar 2. So 315 minus 0.85, which is 2.3. Okay, what do we have? Procedure, parameter, hypotheses, statistic, significance level. Significance level is 5%. Okay, and then evidence for the alternative. Well, the difference in the sample means is technically speaking greater than 0, so we have some evidence already so far. 2.3 is greater than 0. All right, next we're going to check the conditions. So remember, we don't have random sampling, but we did have random sorting, which is equivalent to random assignment. This was an experiment. Okay, so random assignment, check. All right, because it was an experiment, the 10% rule doesn't apply. You only need to check the 10% rule when you are sampling, specifically when you're sampling without replacement. All right, N1 equaled N2 equaled 30, so the central limit theorem satisfies our last condition. All right, moving on to the calculations. So we're going to calculate a standardized test statistic, which follows the same general structure. It's a statistic from our sample minus a parameter. We'll look at the null hypothesis for that, divided by an SD. Okay. Right, when dealing with means, the test statistic you get is not a z-score, it's a t-score. And then our statistic is the difference in the sample means. The parameter is the difference in the true means. And the SD is this square root expression, S1 squared over N1 plus S2 squared over N2. Okay. Right, all of these expressions, like here, here, and here, are going to be on the formula sheet, and you just kind of plug it into the general formula. All right, so the difference, the statistic was 2.3. The parameter is 0. Remember, our null hypothesis is a claim that the value of mu1 minus mu2 is 0. Right, next we'll do the square root of 2.58 squared over 30 plus 1.09 squared over 30. Okay, so I actually calculated this already. It's about 4.5. All right, so that's our test statistic. Okay. All right, next we're going to make a picture. Now, even though this is symmetric and mound-shaped, it's not a normal distribution. This is a T distribution with 29 degrees of freedom. We're going to be using the conservative approach here, where we look at what the degrees of freedom would be from each group separately, and then use the smaller one. Since they're both 30, it doesn't matter which one we pick, degrees of freedom will be 29. All right, 4.5, that's going to be far out in the right tail. Okay, and then we're going to try to find the probability of getting something as extreme or more extreme than that. All right, I'm going to use TCDF on my calculator to figure out that area. I just basically used 4.5 as the lower bound, 999 as the upper bound, and 29 as degrees of freedom. And I got 5.07 times 10 to the negative fifth power. That's the p-value. Okay. In other words, it's approximately 0. Okay, so let's make a conclusion. Since 5.07 times 10 to the negative 5 is less than 5%, we reject the null hypothesis. So yeah, we do have convincing evidence that that the mean number of mistakes found will be greater when people, like these volunteers, are told that the author is a non-native speaker. Okay, I don't want to write all that, so I'm just going to copy and paste it. All right, period. All right, so that was the whole procedure, right? Choose, check, calculate, conclude. So now there's a follow-up question. B, based on your conclusion in part A, which type of error, 1 or 2, could you have made? Explain your answer. Okay. Now, since our decision was to reject the null hypothesis, then we could have only made a type 1 error. All right. Type 1 error is when the null hypothesis is true, but you reject it. Okay, so in context, this means that there is no difference in the mean number of mistakes found by the two groups. Okay, but we said that the first group found more mistakes. Well, okay, I guess we don't really have to explain in context. We just have to explain why it's a type 1 error. So here, use this chart, right? So the truth, right? Null hypothesis, true, alternative, true, and then decision. All right, we could reject the null hypothesis or fail to reject the null hypothesis. All right, that's your type 1. That's your type 2. Okay. Now, because we said we were going to reject, right, look in that row of the table, the only error that you see in that row is the type 1 error.